Hello and welcome to section 2.5.1 lecture video, the beginning of chapter 5. In chapter 5, what we're going to start looking at is the idea of the definite integral. In the last section of chapter 4, we introduced the idea of the indefinite integral, and we're going to talk about how they're related to one another and their applications. So to start out with, what we want to look at is the idea of finding the area under a graph. So for example, if we have the graph as shown here of y equals 1 minus x squared from x equals 0 to x equals 1, we get this region. And if I wanted to find the area of that region, one way I could do it is by approximating it using rectangles. So for example, in letter A here, we're using two rectangles. And what we're doing is we're using the left-hand side of the rectangle to determine the height. So what they did is they broke the region into two equal pieces. So we've got two equal pieces from 0 to 1/2 and from 1/2 to 1. And then the height of the rectangle is determined by the y value on the left-hand side of that region. So it's the y value at 0 and the y value at 1/2. And so the area, to find the area, simple enough, we just use what we know about rectangles to find the area. So in this case, it would be the height, which is 1 for this first rectangle, and the base is 1/2, right? The width of the base. The height of the second one is 3/4, and the width is 1/2. So the area of those two regions together would be base times height, 1/2 times 1, plus base times height. Or, since all these regions are the same width, base, I could do 1/2. I could factor out the 1/2 and do 1/2 plus 1/2 times 1 plus 3/4. Okay, and so if we do that, what we get is 7/8, which is 0.375. Okay, and the more regions we do, the more rectangles we use, the closer to the actual area we're going to get. So we could do the exact same thing we did in A in B, except now with 4 rectangles. So we've got 4 regions now. So we've broken the region from 0 up to 1 up into 4 equal pieces. So they all have a width of 1/4. And their heights are determined by the left-hand side, the y value at the left-hand side. So we got 0, 1. So the height of this rectangle is 1. At 1/4, the height is 15/16. At 1/2, it's 3/4. And at 3/4, it's 7/16. And we can find the area exactly the same way as we did over here. We can take the base times the sum of the heights. So 1 plus 15/16 plus 3/4 plus 7/16. Right, so that's 1 divided by 4 times 1 plus 15 divided by 16 plus 3 divided by 4 plus 7 divided by 16. And that's 0.78125. Hold on, something doesn't sound right about that. Let me check what I put in. Nope, whoops, I put the wrong decimal here. This answer for the first one, I got the correct answer 7/8, but I wrote the wrong decimal. The decimal would be 0.875, and this one is correct. This is 0.78125. So notice the rectangular regions for both of these are bigger than the actual region we're looking for. So by adding in more rectangles, I got a smaller answer that is closer to the actual area of that region. We can also approximate the regions using right-hand endpoints, which in this case would give a lower sum because they're smaller than the picture, and or midpoint sums. So all that changes is not the width of the regions, but the height of the rectangles, because the height is based on either the midpoint of the region or the right-hand side of the region. So in this case, the width is still 1/4, but instead of using the left-hand endpoint of the region, 0 for the first rectangle, I use the right-hand endpoint, 1/4. And so that gives me a height of 15/16. And then we use the right-hand endpoint for this one is 3/4. The right-hand endpoint for this one is 7/16. And the right-hand endpoint for this one would be 0. So plus 0. And when we do that, we get 0.53125. And now notice the rectangles in B were bigger than the region area. The rectangles for C, for this A, sorry, it's another A, are smaller. So we would expect the area of the region to be between these two numbers. And then last but not least, we could do the midpoint idea. So the regions are still 1/4 for a width, but now the height of the rectangle is being taken at the midpoint of the region. So halfway between 0 and 0.25 is 0.125. The height at 0.125 is 63/64. The next region's midpoint is at 0.375. The height at that point is 55/64. At 5/8, the midpoint of the next region, it's 39/64. And for the last region, the height is taken at 7/8, which is 15/64. And when we multiply that all out, we get 0.67185. Now, in this case, this last one is probably the closest to the actual answer, but it's also the hardest one to take because we had to find the midpoint of each region. Whereas for the other ones, we're just looking at the endpoints. So that's the idea. So we can use rectangles to find approximations for these areas. So let's go ahead and take a look at one of these on our own. So it says use a finite approximations to estimate the area under the graph of the function using lower sum, an upper sum, and a midpoint sum for 2 and 4 rectangles. So that means we want to look at the left side, the right side, and the middle. Okay, so let's start by graphing this in the region specified. So let's graph 4 minus x squared between -2 and 2. Okay, so if we go to our graph, we're going to graph 4 minus x squared. And I want to change the domain to only be between -2 and 2. So click and hold on the color dot there, and it should bring up these options. And I want to choose set the domain. And I want to go from -2 to 2. Okay. And then we could zoom in on that a little bit. Okay. So we can see a pretty good graph here. So what I'm going to go ahead and do is I'm going to take a screenshot of this and put it into my notes, or attempt to. Okay, so if we go back to our notes here, okay, perfect. Okay, so now we've got a little graph of what we were looking at here. So on this graph, I can draw some of these regions. So if we wanted to break this apart into 2 rectangles, I'm going to use different colors here. Into 2 rectangles, I would split this into 2 regions. So if I take from -2 to 2 and split it in half, that would happen here at 0. So we'd get a region over here to the left of 0 and a region over here to the right of 0. And the width of those 2 zeros are both 2. Okay. So now what I want to do is I want to draw rectangles with heights based on the left-hand side of those regions and the right-hand side of those regions. So if I were doing the left-hand side of this first region, that would be at -2 here. So the height of the first rectangle would be 0. And then if I do the left-hand side of the second region, that starts at 0, so that would be 0, 4. So the second rectangle would look like this. Okay, so we did that at -2, 0, and 0, 4. So to do a left side region for this one, to find the left hand with 2 rectangles, I would do a width of 2 times my 2 heights together. So 0 plus 4, and so that gives me an area of 8. Okay, so that's if we do the left side. So then if we wanted to try the right side, this time I'm going to use the right hand side of my interval. So my interval goes from -2 to 0, so the right hand side is at 0. So that's where my height's going to be. So we get 0, 4. And that's going to be the height of my rectangle for that region. So my width is 2 and my height is 4. And then for the second one, we're going to start on the right hand side of this interval, which is over here. So that's 2, 0. And so our second rectangle would be flat like that. And so if we add those two together, it would be our width, 2, times the sum of our heights. So 4 plus 0, which is 8. And then last but not least, if we did the midpoint, so the midpoint of this first region is halfway between the two endpoints, -2 and 0, so that would be at 1. So we find the height at 1, so that's -1, so that's -1, 3, and so our rectangle would have that height. And then we do the same thing over here. Our midpoint is 1, so the height is at 1, 3, right? That's the height of the graph at 1. And so our widths are still 2, and our heights for both are 3, so 3 plus 3, which equals 12. So that's doing it with 2 rectangles. Now, if we did the same thing, same idea, but with 3 rectangles, so let me bring in another copy of this graph. Okay, so now we can do it with four rectangles. We want to break our region up into 4 pieces. So in this case, if I break these up into 4, that's every 1 unit. So that's at -2, at -1, at 0, at 1, and at 2. So each one of those has a width of 1. And now it's all about where do we want to do the heights. So if I start with the left side again, I would start on the left side of each interval. So that would be at 0, -2, at 1, 3, at 0, 4, at 1, 3. Okay, those would be my 4 heights. So the first rectangle would be flat. The second rectangle would look like this. The third rectangle would have this height. And the fourth rectangle would have this height. Okay, so we take our width, which is 1, times our heights. So our heights are 0, 3, well, not commas, plus. So our width times the sum of our heights. So 1 times 0 plus 3 plus 4 plus 3. So that would be 10. Okay, so that's the idea. So then for the right side, we do the right-hand side of each interval. So we go to the right-hand tick mark here. So this first one would happen at -1, so that's here. Then the second one would happen at 0, then at 1, and then at 0. So our rectangles would look like this. Okay, so our width is still 1. But our heights now are, the first rectangle is height 3, the second rectangle has height 4, the third rectangle has height 3, and the last has height 0. So that one would also be 10. And then last but not least, if we try and do our midpoints here, okay, the midpoint of this first one is -1.5, so that's right there. The second one is -0.5. the third one is positive 0.5, and the last one is 1.5. And so our rectangles would look something like this. But now we have to find those heights. And you have to find those heights by plugging in the values of our midpoints into the original function. Okay, so the first one would be 4 minus negative 1.5 squared. Okay, so that's 4 minus negative 1.5 squared. Which is 1.75. And then we do that for each one of them. So that's 1.75 plus, and then we could do 4 minus negative 0.5 squared. Which is 3.75. And then you could do the other two, and you would get 3.75 and 1.75. Okay? And so then we do that operation. So it's 1.75 plus 3.75 plus 3.75 plus 1.75 is 11. Okay? And so that's the idea. Now this one was slightly odd because it was this mirrored shape where we had a symmetrical graph. So both the left side and the right side ones ended up being the same. That would obviously not always be the case. So let's go ahead and flip to the next page. If you'd like to at this point, you can pause the video for a second and try this one on your own, and then we'll go through it together. Okay, so now that you've had a chance to try this one, let's try it together. So I'm going to start by graphing it. So we're going to graph x cubed, and we're going to set the domain so that it is between 0 and 1. Okay, so it looks like that. And now I'm going to zoom in on that so that I can see it really well. Make it nice and big. Oh yeah, that's nice. Kind of. Okay. So let's go with that. So screenshot that. Okay, so here's our first graph. So if we're going to do this with two rectangles, we're going to split it in half, right? So start by splitting the graph in half. So this goes from 0 to 1. So splitting it in half would be 0.5. Okay, and the width of each one of those regions is 0.5. Okay, so that's going to be our width for all of these. Okay, so then we can start with the right side. So for the first region, the right side is 0. So there's our first rectangle. And then for the second one, we get 1/2 cubed. Okay, so for this first one, we're going to get 0.5 times 0 plus 1/2 cubed, right? Because I have to plug 1/2, 0.5, the left-hand endpoint into the function. So that's plug that in your calculator and you get 0.0625. Okay, then we can do the left, sorry, that was actually not the right side I just did. That's the left side. Then you can do the right side. Okay, so for the right side, we're talking about the right-hand endpoint. So the right-hand endpoint is at 0.5 and up here at 1. So we get this rectangle and this rectangle. Okay, so that would be our width 0.5 times our right-hand endpoint. The height of that is going to be 0.5 cubed, right? Because that's our right-hand endpoint. And we're plugging into this function y cubed, x cubed. So that's 0.5 cubed plus our right-hand endpoint, which is 1 cubed. Okay, and we can plug that in our calculator. And we get 0.5625. So in this case, our left side would be our lower sum, and our right side would be our upper sum, right? Because our left side is smaller than our right side sum. And so we would expect the actual sum to be somewhere between those. And then we could do our midpoint sum. So the width stays the same, so that 0.5 is going to stay the same, but now where I find the heights are going to be different. So for this one, it's going to be at 0.25. Right? 0.25 is halfway between 0 and 0.5, and for this one, it's going to be at 0.75. Okay, and to find those values, you just plug the midpoint into the function. So this would be 0.5 times 0.25 cubed plus 0.75 cubed. And when we do that, we get 0.21875. Okay, so that's the idea. So then we could do the same thing with our right, with 4 rectangles. So I'll just get another copy of our graph. And so in this case, we want to break this region into 4 regions, right? So we want to go from 0, and the best way to do that is to break it in half, just like we did above, and then break those in half. So that means each one of these, so this is 0.25, this is 0.5, this is 0.75, and this is 1. And each one of these regions is 0.25 across. Okay, our width is 0.25. So for our left-hand side, our width is 0.25, and that's going to be the same for all 3 of these. And now we just find the left hand. So at 0, we get a value. At 0.25, at 0.5, and at 0.75. And that's how we make our rectangle. So the first rectangle is flat. The second rectangle looks like that. Third rectangle looks like that. Whoops, sorry. And the third rectangle looks like this, and the fourth rectangle looks like this. Okay, and so those are just you're gonna take the left-hand endpoint and plug that into the function to get the value. So 0 cubed plus 0.25 cubed plus 0.5 cubed plus 0.75 cubed will get us the area. Okay, and that's 0.140625. Okay, and so to do the right-hand endpoint, the right side, we just use the right-hand endpoint for each region. Okay, so that would be 0.25, 0.5, 0.75, and 1. So 0.25 rectangle looks like this. 0.5, the rectangle looks like that. 0.75, the rectangle looks like this. And 1, the rectangle looks like this. Okay, so we're just taking the right-hand endpoint. So we do the same thing as the one above, except instead of plugging in 0, 0.25, 0.5, 0.75, we plug in 0.25, 0.5, 0.75, and 1, the right-hand endpoints. So 0.25 cubed plus 0.5 cubed plus 0.75 cubed plus 1 cubed. So that's 0.390625. So notice how from the first example, we've increased the left side, the lower sum, and decreased the upper sum. So we're narrowing in on what the actual sum would be. And then for the last one, we need to find the midpoint ones. So you're just going to find the midpoint of each one of these regions, and that's what you're going to plug in for the function. So the midpoint between 0.25 and 1, you just 0, you can just add those two together and divide by 2 to find that. So that's 0.125. The midpoint here is 0.375. The midpoint here is 0.625, and the midpoint for the last one is 0.875. And so you can just plug those into the function, into this expression. So 0.25 times 1.125 cubed plus 0.375 cubed plus 0.625 cubed plus 0.875 cubed. Okay, so now that we've looked at this idea of rectangles, we can apply this to applications. So for example, in this case, we're given the rate at which the scrubbers so a power plant that generates electricity by burning oil, pollutants produced as a result of the burning process are removed by scrubbers in the smokestacks. Over time, the scrubbers become less efficient, and eventually they must be replaced when the amount of pollution released exceeds government standards. Measurements are taken at the end of each month, determining the rate at which pollutants are released into the atmosphere, and recorded as follows. Assume a 30-day month and that the new scrubbers allow only 105 tons per day to be released. Find an upper estimate of the total tonnage of pollutants released by the end of June. What is a lower estimate? In the best case, approximately when will the total of 125 tons of pollutants have been released into the atmosphere? So this works the exact same way that the problems we did before worked. We have a width for each. We subsect the data into regions, in this case months, and we gave each month a number of days. So they're saying assume a 30-day month. Okay, so we're going to say the width of each one of these is 30. And then to get the total, we either use the value from the beginning of the time interval or the end. Now all these values come from the end of the month, so they each pair up with this interval. So to get an upper estimate, we would use the end amounts. So if I want to know an upper estimate for the total tonnage of pollutants released by the end of June, I would simply take the width times the sum of the heights, right? Okay, so that would give me the upper estimate. So we could try that with our calculator. So it was 30 times 0.2, 0.25, 0.27, plus 0.34, 0.45, 0.52. And so we have a total amount of pollution of 60.9 tons. Okay, so that would be 60.9 tons. Now, if we wanted to do these from the beginning, we would use the value at the beginning of each month. So in this case, the beginning of each interval. So in this case, what we would actually look for is the value. We would take the value from the beginning. So these would each get pulled up one. So the value at the very beginning, we were told up here in the problem, which is 0.05. So we would do 30 times 0.05 plus 0.20 plus 0.25 plus 0.27 plus 0.34 plus 0.45. And we would not use the 0.52 because we're using the value from the beginning of the month. So we do the exact same calculation, and I can just get rid of this last number and replace it with 0.05 with the number we're replacing it. So we get 46.8 tons. So because the second number uses the number at the beginning of the month, this would be an underestimate. And because we use the number at the end of the month for the top one, that would be an overestimate. So the true value should be somewhere between the two because of how this works. So that's the first part of the problem. Now the second part says, in the best case, approximately when will a total 125 tons of pollutants have been released into the atmosphere? Well, the best case is this smaller value. So to figure that out, all we have to do is take our answer here and keep adding on to this. So we can take our answer for this one and we would add the next month. So that would be 30. So we can just add it inside the parentheses. So the next month's from the lower estimate would be 0.52. So we could add 0.52. Okay, and that gets us to 62.4. So we're not anywhere close yet. So then we would add the next month. So the next month is 0.63. So 0.63. Still not enough, so we'd add the next month. The next month is 0.70. And we're still not there, but we're getting close, so probably it'll happen in the next month. So the next month would be 0.81. So that's 126.6. So that got us there. So the answer would be, that was for September. So in the best case scenario, we would hit 120 sometime between August and September. Okay, and so that's the idea. So if we use which estimate we choose to multiply by the rate, use gives us a low estimate and an upper estimate, just like when we were talking about the graphs. So you could try a similar thing here. So why don't you guys pause the video for a second and try this one, and when you're ready, you can start it back up and we can go through it. Okay, so now that you've had a chance to try this one, we can try it. So you are sitting on the bank of a tidal river watching the incoming tide carry a bottle upstream. You record the velocity of the flow every 5 minutes for an hour, with the results shown in the accompanying table. About how far upstream did the bottle travel during that hour? Find an estimate using 12 subintervals for length 5 with a left endpoint values and then with the right endpoint values. So here are our intervals: 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30, and so on. Okay, these are our intervals. Okay, So when we go it, we can either take, for the interval 0 to 5, we can either use 1 or 1.2. So the 1 would be the left-hand endpoint, and the 1.2 would be the right-hand endpoint. So we could get two different answers just like before. So we take our width, and we multiply it by the sum of our endpoints. So we do 1 plus 1.2 plus 1.7 plus 2 plus 1.8 plus 1.6 plus 1.4 plus 1.2 plus 1 plus 1.8 plus 1.5 plus 1.2. Okay, so we could add that up. So that's 7, 15, 16, 17, 21, 27, 35, 42, 44, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So that should be 5 times, shoot, I lost it. Trying to do that in my head. So let's go ahead and just use the calculator. So it would be 5 times 1 plus 1.2 plus 1.7, 2.0, 1.8, 1.6, 1.4, 1.2, I think I got. Yeah, so I think I got them all. So for that one, we got 87. Meters. And then we could do the same thing, but this time we're going to use the upper S, the right side. So for 0 to 5, we'll use 1.2. From 5 to 10, we'll use 1.7. So this would be 5 times 1, 0.2 plus 1.7 plus 2 plus 1.8 plus 1.6 plus 1.4 plus 1.2 plus 1 plus 1.8 plus 1.5 plus 1.2 plus 0. Okay, so this time we use those endpoints. So what we could do is get rid of the first one here and just replace it with a 0. And so for that one, we get 82. So we could guess that the actual total distance is somewhere between those two values, between 87 meters and 82 values. Okay, so that's the idea. Now the last thing in this section is the idea of average value of a function. Now average value of the function works the same way, except instead of, we find the total area and we divide it by the width of the region. Okay, so you find the total area and then divide it by the width of the region. Okay, so it says use a finite sum. So it's the area divided by the width of the whole region. So use a finite sum to estimate the average value of f on the given interval by partitioning the interval into 4 subintervals of equal length and evaluating at the subinterval midpoints. Okay, so in this case, we're going from 0 to 4. So that would be 0 to 1, 0 to, I mean, sorry, not 0, 1 to 2, 2 to 3, and 3 to 4. And so to do this one, the width of each region is 1, so we're going to take 1 times, and then we're going to find the midpoints of these. So the midpoints are 0.5, 1.5, 2.5, and 3.5. Okay, and then we're going to plug those values into the function to get the y values that go inside the parentheses. So it would be, 1 minus the cosine of pi over 4, pi times 0.5 over 4 to the 4th, plus 1 minus cosine of pi times 1.5 over 4 to the 4th, plus 1 minus cosine of pi times 2.5 over 4 to the 4th, plus 1 minus cosine of pi times 3.5 over 4 to the 4th. Okay, and that's going to give us, and then we want to divide that whole thing by the width of the region, which is simply 4 minus 0. Okay, so we can try and put that in our calculator. So we're going to do a division, so it's 1 times 1 minus the 1 minus the cosine of pi times 0.5 divided by 4 to the 4th, plus 1 minus cosine of pi times 1.5 divided by 4 to the 4th, plus 1 minus cosine of pi times 2.5 divided by 4 to the 4th, plus 1 minus cosine of pi times 3.5 divided by 4 to the 4th. Okay, and then close the parentheses, and then we're going to divide that by 4 minus 0. Okay, and I think the thing it doesn't like is that I didn't put multiplications in here. So let's go ahead and add those back in and see if that fixes my problem. Okay, it does. And so it tells me the average value here is 0.00, except I'm in degrees, so let's change that to radians because we're dealing with this. So it's 0.625, or in a fraction, 5/8. So 0.625 or 5/8. Okay, so that's all there is to that. So the idea here is, instead of finding the total area, we're finding the average value of the function. So we can do it the same idea, the same way, but in the end, we have to divide by the total width so that we get the average value. Okay, so at this point, if you want, you can go ahead and pause the video and give this last one a try, and then when you restart the video, we'll go back, go through it together. Okay, so we're doing the same idea here. We need 4 regions, so if I divide 1 to 9 into 4 equal regions, I get 1 to 3, 3 to 5, 5 to 7, and 7 to 9. And so the midpoints are 2, 4, 6, and 8. And the width of each region is 2. So this would be 2 times, and then we just plug each one of these numbers into the function and add them together. So 1 over 2 plus 1 over 4 plus 1 over 6 plus 1 over 8 divided by the total width of the region, which is 9 minus 1. Okay, so that one's going to be a little easier to put in the calculator. So we're doing a fraction, so 2 times 1/2 plus 1/4 plus 1/6 plus 1/8 divided by 9 minus 1. Okay, and that gave us 25/96.